Welcome dear learners. We are continuing Unit 2 Chemical Bonding and Molecular Structure. In the present module, we are discussing molecular orbital theory of heteroatomic molecules. The contents of this module are heteroatomic molecules, molecular orbital diagram, bond order and magnetic behavior of nitric oxide, carbon monoxide, hydrogen fluoride, hydrogen chloride and lithium fluoride molecule. Finally, we have problems based on these concepts. First of all, we are discussing heteroatomic molecules. You are familiar with homoatomic diatomic molecules and heteroatomic diatomic molecules. Now we are emphasizing on heteroatomic molecules. Heteroatomic molecules, the word hetero means different. So in a heteroatomic molecule, there are more than one type of element. This is the definition of a heteroatomic molecule. A heteroatomic molecule is a molecule that consists of atoms of at least two different elements. For example, HBr, HCl, H2O, etc. In HBr, there are two elements, namely hydrogen and bromine. In HCl, the two different elements are hydrogen and chlorine. And finally, in water, the two elements are hydrogen and oxygen. So, a molecule with two different type of atoms can be considered as a heteroatomic molecule. They may be diatomic, triatomic or polyatomic. Now, a diatomic molecule with two non-identical atoms are called heteronuclear diatomic molecules. When atoms are not identical, the molecule forms combining atomic orbitals of unequal energies. This is very important as far as the MO diagram of heteronuclear molecules are concerned. For example, HF, carbon monoxide, NO, LIF, etc. provides good illustration for heteronuclear diatomic molecules. Now, MO diagram. You learned the concept of molecular orbital diagram. You are familiar with the fact that the molecular orbital diagram or MO diagram is an arrangement of various molecular orbitals in the increasing order of their energy. You know the fact that molecular orbitals are formed by the overlapping of atomic orbitals. You are familiar with sigma 1s, sigma star 1s, sigma 2s, etc. And it is possible to arrange the molecular orbitals in the increasing order of their energy to get a diagram called the molecular orbital diagram. We are now just revising the concept of the molecular orbital diagram. The molecular orbitals are formed by the overlapping of atomic orbitals. It is possible to arrange these molecular orbitals in the increasing order of their energy to get an energy level diagram or the molecular orbital diagram. The obtained energy level diagram is named as the MO diagram, and the MO diagram for homonuclear diatomic molecules with regular energy order is shown here for your reference. This is, I am showing here to just revise the concept of the molecular orbital diagram of homonuclear diatomic molecules with a regular energy order. We have to just revise that concept and then we can only move to the molecular orbital diagram of heteronuclear diatomic molecules. This is the MO diagram. Here in this MO diagram, you can see left side and right side shows the atomic orbitals, which is shown in the increasing order of their energy. You can see 1s orbital, 2s orbital, 2p orbital, etc. They are atomic orbitals, and at the middle portion, you can see the presence of sigma 1s, sigma star 1s, etc. They are the molecular orbitals. So, in an MO diagram, we are representing atomic orbitals also for a convention, for a comparison also. The molecular orbitals with lower energy than atomic orbitals are called bonding MOs, and those with energy higher than that of atomic orbitals are said to be ABMOs. You can see the presence of BMOs, ABMOs, etc. in this MO diagram. This I am showing just to revise the concept of the MO diagram. Now, energy order is very significant as far as we are discussing the concept of bond order, etc. The regular energy order of molecular orbitals are sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, followed by pi 2px equal to pi 2py. Here you can see that these two orbitals have a similar energy. That means they are doubly degenerate. Then pi star 2px equal to pi star 2py, they are also doubly degenerate. Doubly degenerate means two orbitals have the same energy. That situation is referred as doubly degenerate condition. And finally, the highest energy orbital, that is nothing but sigma star 2p is Z. This is the energy order of 10 molecular orbitals, which is the regular energy order. Now, exceptional configuration. It should be noted that you have to revise the concept that in the case of second row elements up to nitrogen, the energy of the sigma 2pz orbital is slightly higher than that of pi 2px and pi 2py. This shows some exception, and this is called exceptional configuration, and this is only possible in the case of the second row elements up to nitrogen. Hence, we can rewrite the energy of such molecules as this is the new order, or this is the exceptional configuration or exceptional arrangement for elements up to nitrogen in the second row of the periodic table. This is the exceptional order. Here you can see sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, then pi 2px equal to pi 2py, and you can see that the energy of the sigma 2pz is slightly higher than pi 2px equal to pi 2py. After sigma 2pz, you can see pi star 2px, which is equal to pi star 2py, and finally sigma star 2p is Z. So you now revised the concept of regular MO order, regular energy order of first 10 molecular orbitals, and exceptional order of first 10 molecular orbitals. Now we are focusing on the core topic of this discussion, that is nothing but molecular orbital diagrams for heteronuclear diatomic molecules. I just mentioned you the fact that a heteronuclear molecule is a molecule which contains more than one type of element, and a heteronuclear diatomic molecule is a molecule that consists of two different atoms of two different elements, and there are a total of two atoms, and these atoms belongs to two different elements. Such a molecule is heteronuclear diatomic molecule, and we are now giving emphasis to MO diagrams for such molecules. The MO diagram of a heteronuclear diatomic molecule is approached in a similar way to that of homonuclear diatomic molecules. The orbital diagrams will not be symmetrical in this case. It is a very important point as far as we are discussing MO diagrams of heteronuclear diatomic molecules. The point is that the MO diagram will not be symmetrical. The major difference is that the more electronegative atom will have orbitals at a lower energy level. This is the major difference between molecular orbital diagram of a heteronuclear diatomic molecule from homonuclear diatomic molecule. Now let us have a glimpse on the molecular orbital diagram of some heteronuclear diatomic molecules. First of all, we are focusing on molecular orbital diagram of the heteronuclear diatomic molecule NO, that is nitric oxide. Nitric oxide is a heteronuclear diatomic molecule. You can see here there are two atoms. One is nitrogen atom, and the next one is a different atom, that is nothing but oxygen. So NO provide a good example for a heteronuclear diatomic molecule, and we are now looking on MO diagram of NO molecule. Nitric oxide is a heteronuclear diatomic molecule. The atomic number of the first element, first atom, nitrogen, is 7, and its electronic arrangement is 1s2 2s2 2p3. And the second atom is oxygen. Its atomic number is 8, and electronic arrangement is 1s2 2s2 2p4. Thus, in the case of nitric oxide molecule, you can have a total of 15 electrons. That means, in the MO diagram of nitric oxide molecule, you have to accommodate a total of 15 electrons. Because of high electronegativity of oxygen, the atomic orbital of oxygen would be lower in energy than the corresponding atomic orbitals of nitrogen. That's why the MO diagram of nitric oxide molecule will not be symmetrical. the BMOs would have more characteristics of atomic orbitals of oxygen and ABMOs would have more characteristics of atomic orbitals of nitrogen. This is because in NO molecule, oxygen is more electronegative and its energy, the energy of the atomic orbitals of oxygen is lying just below the corresponding atomic orbitals of nitrogen. That means whenever we are looking onto the MO diagram, you can see that the BMOs or bonding molecular orbitals have more characteristic features of atomic orbitals of oxygen, whereas antibonding molecular orbitals would have more characteristics of the less electronegative atom, that is nitrogen. Now, this is the molecular orbital diagram of nitric oxide molecule. At the left hand side, you can see the atomic orbitals of nitrogen, and I am showing here the 2s orbitals, or the diagram is just beginning from the 2s orbital and 1s orbital is just excluded for the convenience for showing here. So, 2s2 2p3 is the outer shell configuration of nitrogen. Similarly, for oxygen atom, which is shown on the right hand side, the electronic arrangement is in the outer shell is 2s2 2p4. So, we have to accommodate these electrons, and the MO diagram or the molecular orbitals of NO molecule is shown at the middle portion, and the electrons are filling in this arrangement. So, this simply depicts the MO diagram of the nitric oxide molecule. It is very well clear that the atomic orbitals of oxygen lies just below the energy level of the atomic orbitals of the nitrogen atom. See, for instance, this is the 2p orbitals of nitrogen, and it is higher in energy when compared with the 2p orbitals of the oxygen. Now, we have to consider the bond order value, which is of prime importance as far as the stability, bond length, etc. of a molecule is concerned. The MO configuration can be written from this MO diagram, and the complete MO configuration of NO molecule is here: sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2 equal to pi 2py2, then sigma 2pz2, and finally one electron is present in pi star 2px. That's why we are representing pi star 2px1. Here you can see the presence of total of 15 electrons. The 15 electrons is because of the fact that atomic number of nitrogen is 7 and atomic number of oxygen is 8. So, you are having a total of 15 electrons that has to be accommodated with this electronic arrangement. Now, we can calculate the bond order. The bond order is equal to half into number of bonding electrons minus number of anti-bonding electrons. Here it is clear that the number of bonding electrons is equal to 10, and anti-bonding electrons which are present in the orbitals with the star, that is the starred orbitals, are antibonding molecular orbitals. So, here you can see there are 5 antibonding electrons, and the bond order of this molecule is equal to half into 10 minus 5, that is equal to 2.5, and this NO molecule is stable because this 2.5 is a positive value. A positive value of bond order indicates that the molecule is stable, and the bond energy of NO molecule is theoretically calculated and experimentally proven, and that is equal to 667.8 kilojoule per mole, and this about the bond energy of NO molecule. Now, we are focusing on magnetic behavior of nitric oxide. In order to illustrate the magnetic behavior, or in order to represent or predict the magnetic properties of the nitric oxide molecule, we have to look on the number of unpaired electrons present in the molecular orbitals. So, looking onto the MO configuration and MO arrangement, you can see the presence of one unpaired electron which is present in pi star 2px orbital, and owing to the presence of this one unpaired electron, it is very well clear that the molecule NO, nitric oxide molecule, is a paramagnetic molecule. Now, we are entering into another heteroatomic diatomic molecule, that is nothing but carbon monoxide, and we are now focusing on molecular orbital diagram of carbon monoxide. The atomic number of the first element carbon is 6 with electronic arrangement 1s2, 2s2, 2p2, and the atomic number of the second element oxygen, that is 8. The configuration is 1s2, 2s2, 2p4. So, in the MO diagram of carbon monoxide molecule, a total of 14 electrons are to be accommodated in the molecular orbitals of the carbon monoxide molecule. Now, because of the higher electronegativity of oxygen, its atomic orbital would be lower in energy than the corresponding atomic orbitals of carbon atom. Due to this energy difference, the bonding and antibonding molecular orbitals will receive different contribution from atomic orbitals of carbon and atomic orbitals of oxygen. The BMOs will receive more contribution from atomic orbitals of low energy orbital, that is atomic orbitals of oxygen. The BMOs would have more characteristics of atomic orbitals of oxygen and ABMOs would have more characteristics of atomic orbitals of carbon. This about the sketch of molecular orbital diagram of carbon monoxide molecule. Left hand side and right hand side represents atomic orbitals of carbon atom and atomic orbitals of oxygen atom. Only outer shell arrangement is shown here, and the center portion represents the molecular orbitals of the carbon monoxide molecule. You can see the electrons are filling in the increasing order of their energy, both in MOs as well as in atomic orbitals of each element. Now, we have to consider the bond order of carbon monoxide molecule. On looking into this MO diagram, we can write the MO configuration of the carbon monoxide molecule as sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, then pi 2p x2 equal to pi 2p y2 and sigma 2p z2. This is the arrangement of the 14 electrons in the molecular orbitals, and based on this electronic configuration, it is possible to compute the value of the bond order, and the bond order value is equal to half into 10 minus 4, that is equal to 3. The carbon monoxide molecule depicts a positive value of bond order 3, and this positive value of bond order 3 indicates that the carbon monoxide molecule is a stable molecule and the bond energy is 1067 kilojoule per mole. Now we are focusing on magnetic behavior or magnetic property of carbon monoxide. This is the MO configuration, and on careful looking onto the molecular orbitals, you can find out whether there is unpaired electrons or not. It is very well clear that all the electrons are paired in the molecular orbitals of carbon monoxide. Thus we can say that carbon monoxide molecule is a diamagnetic molecule. Carbon monoxide molecule is diamagnetic in nature. Now we are discussing another heteroatomic diatomic molecule, that is hydrogen fluoride. We are now focusing on molecular orbital diagram of hydrogen fluoride molecule. In the formation of hydrogen fluoride molecule, only the 2p electrons of fluorine atom would combine effectively with the solitary electron of the hydrogen atom. You know that for the hydrogen atom, the electronic arrangement is on its own, and you can see that there is only one electron, and that one electron overlap with the or bond undergo bond formation with the half-filled 2p orbitals of the fluorine atom. So there occur interaction between 2p electrons of fluorine and the one and only electron of the hydrogen atom. Only a pz orbital is able to combine with an s orbital. This is from the condition for effective overlap that we have studied in the previous modules. The combination of a px or a py orbital with an s orbital is ruled out on symmetry considerations. That means a pz orbital can form effective overlap with s orbital of hydrogen. Thus, the 2pz orbital of fluorine gives a highly effective overlap with 1s orbital of hydrogen atom to form sigma bonding molecular orbital and sigma star anti-bonding molecular orbital. The MO diagram of hydrogen fluoride molecule can be drawn like this. Here you can see the left hand side, the one electron present in the hydrogen atom, that is the atomic orbital of hydrogen is shown on left hand side, and the configuration is 1s1, and it undergo overlap with the 2p z orbital of the fluorine atom. The 2p orbitals of the fluorine atom are shown here. 2px2, 2py2 and 1 electron is present in 2pz orbital. That half-filled orbital undergo overlap with the half-filled orbital of the 1s arrangement of hydrogen, and here there occur the formation of bonding molecular orbital and antibonding molecular orbital. This 2s just carried out here, but that is not the molecular orbital. This is the 2s orbital of the fluorine atom. I just carried out here. This is not needed to represent in the MO diagram, but this 2s is the outer orbital. That is why I am representing here. 2s can be carry over towards this position. That is not the molecular orbital. Similarly, the 2px and 2py are also carry over here, but the exact part of this diagram is the representation of sigma bonding molecular orbital and sigma star antibonding molecular orbital. This sigma bonding molecular orbital is formed by the overlapping of 1s orbital of hydrogen with the 2pz orbital, half-filled 2pz orbital of the fluorine atom. So, bonding molecular orbital is marked as sigma, and in a similar way there occur the subtraction overlap, and that leads to the generation of the sigma star antibonding molecular orbital. So, sigma molecular orbital and the sigma star antibonding molecular orbital are formed from 1s orbital of hydrogen with the 2pz orbital of fluorine. And here you can see the electronic arrangement. In hydrogen, there is only one electron is take part in chemical bonding with the fluorine atom. In fluorine atom, there is also one electron. So, that two electrons are filled in the sigma bonding molecular orbital, and you cannot see any electron in the antibonding molecular orbital. Now, we are entering into the bond order of this HF molecule. MO configuration can be written as sigma 2 and sigma star 0, or it can be otherwise represented as sigma sp2. This can also be marked as sigma sp. Why we call it a sigma sp? Sigma sp is because that bonding molecular orbital is formed by the overlapping of s orbital of hydrogen and p orbital of fluorine. That's why you can mark it as sigma sp instead of sigma. Both the notations can be used. So, the MO configuration is sigma 2, sigma star 0, or sigma sp2 and sigma star sp0. It is possible to calculate the bond order value of the hydrogen fluoride molecule like this, that is equal to half into 2 minus 0. 0 is because there is no electron is present in the antibonding molecular orbital, and you will get a bond order value of 1, and this positive value of the bond order indicates that the HF molecule is stable, and the bond energy is also calculated theoretically and verified experimentally, and that is equal to 565 kilojoule per mole. Now, the magnetic response or magnetic behavior of the hydrogen fluoride molecule. From the MO diagram, it is very well clear that no unpaired electrons are present in the molecular orbitals. Since all electrons are paired in the molecular orbitals, HF molecule is a diamond. Considering the molecular orbital diagram of another heteroatomic diatomic molecule, that is HCl or hydrogen chloride. In the formation of HCl molecule, only the 3p electrons of chlorine atom would combine effectively with the 1s electron of the hydrogen atom. Only a pz orbital is able to combine with an s orbital, as I just mentioned in the case of the hydrogen fluoride molecule. Now, the combination of a px or py orbital with an s orbital is ruled out due to symmetry considerations. Thus, the 3pz orbital of chlorine gives a highly effective overlap with the 1s orbital of hydrogen to form sigma BMO and sigma star antibonding molecular orbital. The MO diagram of hydrogen chloride molecule can be represented like this. Here in the MO diagram, you can see the 1s orbital of 1s atomic orbital of hydrogen and 3s as well as the 3p atomic orbitals of the chlorine. Now, you have to focus on the 3p atomic orbital. The electronic arrangement is 3p5. So, I can mark it as 3px2, 3py2 and 3pz1. So this one unpaired electron, for the sake of convenience, let it be present in 3pz, and this is 1s, and there is an overlap between this 1s orbital and 3pz orbital of chlorine to form a sigma bonding molecular orbital, which is abbreviated as sigma sp, and a sigma star sp, which is nothing but anti-bonding molecular orbital. So this is the MO diagram of hydrogen chloride molecule, and based on this MO diagram, we can calculate the bond order of HCl molecule also. The MO configuration can be written from this MO diagram, and the MO diagram depicts the MO configuration as sigma 2 sigma star 0, or simply sigma sp2 sigma star sp0. The notation sigma sp is because of the fact that bonding MO is formed by the overlapping of 1s orbital of hydrogen with the 3pz orbital of chlorine. So that orbital, that bonding orbital is abbreviated or notated as sigma sp instead of sigma. Both the notations can be used for convenience. Now the bond order value is equal to half into 2 minus 0, which is equal to 1, and that simply implies that the HCl molecule is a stable molecule. Bond energy of HCl molecule is theoretically calculated and experimentally proven, which is equal to 431.5 kilojoule per mole. Now we are discussing the magnetic behavior of the HCl molecule. In this MO diagram, you cannot see the presence of any unpaired electron in the molecular orbital. Since all electrons in the molecular orbitals of hydrogen chloride are paired, HCl is said to be a diamagnetic molecule. Now we are discussing the last heteroatomic diatomic molecule, its MO diagram, that is nothing but MO diagram of lithium fluoride. In the formation of lithium fluoride molecule, only the 2p electrons of the fluorine atom would combine effectively with the 2s electrons of the lithium atom. Only a pz orbital is able to combine with an s orbital. The combination of a px or py orbital with an s orbital is ruled out due to symmetry considerations. This point we have discussed in the previous two examples. The 2pz orbital of fluorine gives highly effective overlap with the 2s orbital of lithium to form sigma bonding molecular orbital and sigma star anti-bonding molecular orbital. MO diagram of lithium fluoride molecule is shown here. In this MO diagram, you can see the atomic orbitals of the lithium, preferably the 2s orbital. You can see the 2s on arrangement, and the 2p5 arrangement of fluorine is also shown here. The overlapping is happened between the 2s orbital of lithium with the 2pz orbital of fluorine, and the bonding molecular orbital is marked as sigma. You can also be represented as a sigma sp, and the antibonding molecular orbital is notated as sigma star. You can also represent it as sigma star sp. This is because the MOs, BMOs and ABMO is formed by the overlapping between s and p orbital, as I mentioned in the case of HF and HCl. Now the bond order of the lithium fluoride molecule. From this MO diagram, it is possible to represent the MO configuration as sigma 2 sigma star 0, or sigma sp2 and sigma star sp0. And from this MO diagram, it is possible to calculate bond order is equal to half into 2 minus 0, that is equal to 1. So the positive value of the bond order simply represents that the LIF molecule is a stable molecule. Moving on to the bond energy of this LIF molecule, its value is 1023 kilojoule per mole. Now the magnetic response or magnetic behavior of lithium fluoride molecule, in the MO diagram it is very well clear that no electrons are present as unpaired, or no unpaired electrons are present. Since all the electrons in the MO molecular orbitals are paired, you can say that the lithium fluoride molecule is a diamagnetic molecule. Now we are focusing on some problems based on the concept we have learned so far. The first multiple choice question is this: in hydrogen fluoride molecule, which atomic orbitals primarily form the bonding molecular orbital? Hydrogen 1s and fluorine 2s, hydrogen 1s and fluorine 2p, hydrogen 2s and fluorine 2p, hydrogen 1s and fluorine 3p. On careful analysis, you will get the correct answer as hydrogen 1s and fluorine 2p. More legibly speaking, 1s orbital of hydrogen with the 2pz orbital of fluorine. Therefore, your answer is option B. Moving on to next MCQ. What is the bond order of carbon monoxide according to molecular orbital theory. You know the fact that carbon monoxide is a species with 14 electrons, and based on that you can write the MO configuration. From that you can calculate the bond order also. That concept we have studied in this module itself, and these are the options 1, 2, 2.5 and 3. It is very well clear that the bond order of carbon monoxide molecule is 3, and your answer is option D, 3. Another MCQ, which of the following molecule is paramagnetic? It is possible to predict the magnetic property based on number of unpaired electrons present in the molecular orbitals. These are the options of this question. Option A, carbon monoxide. Option B, nitric oxide. Option C, hydrogen chloride. And option D, hydrogen fluoride. On careful analysis of the MO configuration and the total number of electrons, it is very well clear that option B, that is nitric oxide, is a paramagnetic molecule. NO molecule is paramagnetic due to the presence of one unpaired electron in the molecular orbital. Another multiple choice question. What is the bond order of NO plus ion? These are the options. Option A, 1. Option B, 2. Option C, 2.5. And option D, 3. In NO plus, you can say that you can consider the fact that there are a total of 14 electrons. This is because in NO there are a total of 15 electrons. For nitrogen, atomic number is 7, and for oxygen, atomic number is 8. So in NO molecule, in neutral NO molecule, there are 15 electrons. But the question is about NO plus. So it has one electron less than neutral NO molecule. So NO plus is a molecule with 14 electrons. If the number of electrons is equal to 14, in the previous modules we have discussed a chart. If the number of electrons is equal to 14, you can very easily say that the bond order will be equal to 3. So your answer is option D, bond order value equal to 3. This is the last multiple choice question of this module. When NO is changed to NO plus, these are the options. Option A, bond order increases and changed to diamagnetic. Bond order decreases and changed to paramagnetic. Bond order increases and changed to paramagnetic. And the last option is bond order decreases and changed to diamagnetic. It is clear that NO molecule is having a total of 15 electrons. It is paramagnetic. It is having a bond order of 2.5. In NO plus molecule, there will be no unpaired electron. Total number of electrons will be equal to 14, and the bond order value is equal to 3. So you can arrive at the final answer as option A, bond order increases from 2.5 to 3, and NO plus, which is the result of removal of electron from NO plus molecule is a diamagnetic molecule. So the answer is option A. That's all about the discussion on the present module. Have a nice learning experience. Thank you.